So next up is Quentin Monet, who will be presenting stateful packet processing and OpenState implementation with eBPF. Quentin?
Okay, thank you. Thanks for coming. So, I'm Quentin, I work at Stateful, and I've come to talk about the OpenState interface for stateful packet processing and about the possibility to implement it with eBPF, among other solutions. So the initial plan was to talk a lot about eBPF and to present it. And at some point, I somewhat changed my mind. So it will be a bit less about eBPF and more about OpenState. So just before we get to the technical details, we are working in software-defined networks, so we have physical hosts, we have virtual machines, we have programmable switches and controllers. So controllers are used to configure the switches in a centralized way. Regarding data path, we have two paths for data. This is kind of shortcut when all packets are processed by the programmable switch. And for packets that require more processing tasks, more processing operations, they are usually raised as exceptions and sent to the controller. So this is the case for every packet belonging to stateful flows. By stateful, I mean flows for which the forwarding decision will depend on the traffic that has been previously observed in the switch. So the idea behind this talk is, what if we could take as many packets as we can from this standard path and move them to this faster path, to this shortcut path. So can we find a way to make the switch smart enough to do that while keeping this centralized way to configure everything? So this is also the idea behind the eBPF project, which is a European research project that has started in January 2015. It's expected to close next month, actually, so we are near the end of the project. And the idea is to get higher speed reactive control and processing tasks inside the switches, while keeping this centralized control, while being scalable, but then everyone wants to be scalable, so it's nothing new. And we want also to be platform independent, so not to rely on any specific hardware or vendor solution. So as for the partners of the project, it's a research project, so we have business companies, we have also academics partners on the right side. And all those partners have designed what we call the Rpp Architecture, or Rpp switch. And it's made of three components. There is OpenState for stateful processing. We'll talk about it just after that. There is something for in-switch packet generation, but we will not see it in the presentation. And there's also Open Packet Processor, which is an extension based on the two other components. And we'll see a little at the end of the presentation. So OpenState, it's for stateful packet processing. And the concept is to forward packets depending on what we have seen already. So what we need is to keep states for the traffic. So we will need, when a new packet arrives, we will need to perform a lookup for the state the flow it belongs to is in. And then we will need a second lookup somewhere to find what action we must do for the state. And then the first step of the process is to update the state of the flow to a new value that we will obtain from the second lookup as well. So for this we need two tables, the state table, the first one on the left, and the XFSM table. It stands for Extended Finite State Machine, which is the mathematical model implemented by this process. So here's a case study for seeing how it works. Concretely, we try to do port knocking. So usually port knocking consists in a server telling to everyone that it port, for example, SSH port 22 is closed, and only when a client sends a correct secret sequence of packets, then the server says, okay, it's open for you, you can connect to this port, so it's a security measure. So to implement this sequence, for example, in my case, packets on UDP port 1111, 2222, and so on until 4. To implement this, we need to register somewhere the state while to remember the previous packets from this sequence. So this is the diagram, the state machine for this example. We start in the initial state here, when the port is closed, when we receive the first packet of this sequence, we move to state 1, 2, 3, and then we open the port, the SSH port. And if we find a packet in between that's not part of the sequence, we go back to the initial state. So this is the state table for this example. At the beginning of the program, it's nearly empty. We just have a rule that says that for all flows, we are in the default state, so that's the initial state here. So when a packet arrives, we get state default initial for this packet, and then we perform the second lookup in the XFSM table. So in this table, depending on the packet we receive, we will match on a state and on an event. For example, the event is UDP destination port 1111. In this case, so if we have the default state and the correct port, we will return an action, which is drop the packet. We don't want to forward this packet. It just in the switch we drop it, then into reach the server. And we will move to the next state, which is state 1. If the packet is not part of the sequence, otherwise it's not, in other words, it's not the correct port, or it's not a state we know, we just have a default rule at the end that reinitiates the state of the packets. So we get this value, we perform this action on the packet, and we update the state table with the new state we got for this flow. So after the update operation, for example, if the packet was part of the sequence, we will have a new rule with the correct metadata for this flow and the new state we found. So that's quite simple. So we have a variety of implementations for this in the project, and the questions we try to answer to for my part was, can we do this with eBPF? So eBPF, I won't dig into the details again. We have had 2 good presentations already, thanks to Daniel and Thomas. So here is again the same diagram that you saw with the CBM presentation. So I'm using TC hooks to attach program inside the kernel. I can compile my program from a C subset of code, and I can also communicate with user programs through maps. And that will be very important, because by default, so the BPF program, when it runs, it processes a packet, and then once it's finished, we lose everything about its state. It's discarded, and then when the next packet arrives, we start anew with nothing. So we have maps. And as Thomas said already, we can keep states with those maps because they are persistent between different instances of the program. They can also be shared amongst multiple programs. I don't care, but they can also be shared with user space, and this will enable us to initialize the maps. So let's go. Let's use hash maps for the OpenState tables. So the code corresponding to this is on GitHub if you want to have a look at this more in details. So I use the first file, which is my header file, OpenState.h, in which I have the key and value for the state tables, the key and value structures. I'm using ether type, IP source, IP destination, and my state table will return a value for the current state of this flow. I also have the XFSM table below, so I will match on, again, properties I want for the event, and also the state I got from the first table. And then this second table will return both an action to perform on the packet and the next state to update the first table. That's the file for a program. So part of this file, obviously, I skipped everything about header processing. So I just jumped to the state table lookup. So I have to set a key, and then to perform my lookup with one of the eBPF helper functions from the kernel that make it able to accept the maps. If I get a return value from these maps, then I go to the XFSM lookup. Otherwise, but I should not reach this point, I go to the end of program and returns some kind of error code. This is the next part. I would have to perform the second lookup in the XFSM table. So I set up again a key. I perform my lookup, and depending on the value, if I got something, I will first update the state in the state table for this flow. So I will use the next state I got from the XFSM table to perform the update, and after that I can just switch on the action I got from the XFSM table. So action drop, then I send the code for TC action shots for telling TC that he has to shut down the packet, and otherwise I can forward it. So this is nearly all for the code. So we can compile it with Clang. That's the command line I use. We can attach it to a QDisk as a BPF filter. And the only thing we have to do after that is to initialize the maps. So I have not provided the code in the slides. We can use a user space program that relies on BPF system calls to fill the maps from user space. Also, there are tools known as BCC tools, BPF compiler that use Python wrappers to do it in a probably easier way, but it's not necessary, so we can do both. Okay. So I don't have time for a demo, but this is just a screenshot of what I got for port knocking. It's not really impressive. So I send packets on port 22, then the correct sequence, then again packets on port 22, and only the last packets, P7, P8, P9, pass through the port knocking application. After port knocking, I just have another second use case, which is a token bucket, which is maybe more interesting from the industrial point of view than port knocking. The thing is with this OpenState interface, I cannot exactly implement a classical token buckets, bucket with tokens, and each time a packet arrives, a token is consumed, and when we have no more token, we cannot forward any more packet. It's a rate limiter use case. So I cannot do this as a bucket with a counter for tokens. I have to find another way to implement it because of the operation for OpenState. So I'm using an equivalent algorithm with a time window that shifts to the right one slot at a time. And I have three cases. So if the packet arrives between the time boundaries of this window, it's okay, it's normal traffic, I can forward this packet. And then I move the window from one slot to the right. If the packet arrives too late for the window, it means that we have not seen a lot of packets during the last period because we have not shifted the window much. So it's okay, we can forward also the packet. And we will initialize the position of the window to the current position of the packet. And the last case is in case of heavy loads. When there are many packets arriving on the same time slot, then we have shifted the window too much on the right, so there is no token left for this packet. So we drop the packet and do not move the window. So we also need more things on the building side. We have to use the extension of OpenState. It's called Open Packet Processor. So it's an extension. So we will use everything from OpenState plus global and per flow registers, which are like variables. And these registers are evaluated with a set of conditions. And those conditions, the result of those conditions, will be used to match for the match in the XFSM lookup. So for token bucket, we have two registers, tmin and tmax, that correspond to those values here and there that define the boundaries of the time window at every moment. So we can have conditions with those values, those variables, and we can evaluate those conditions, and depending on the result, true or false of those conditions, we will match or not in the XFSM table. So this is the full diagram of Rpp Architecture. Without entering too much into the details, first we process the packet to extract any information we need to match, and we perform the first lookup in the state table. So on this packet metadata, we get the state for the flow and also a set of registers. With those registers and possibly global registers, we evaluate the conditions that we want to use. And then the second lookup is done on the result of those conditions, the state we are in, and the packet events, for example, the UDP port for port knocking. And it returns as before the next state for the flow, the action to perform on the packet, and also an update function that will be used to update per flow and global registers. So on the eBPF side, we have nearly everything we need already. We need to add those registers, those conditions. Also for the token bucket, we need the arrival time of the packet. There is an internal helper for this, so it's quite useful. And the conditions can be defined in each program. So for example, in my program, I first get the arrival time of the packet. I perform my state lookup. And then I evaluate conditions, so I've implemented a wrapper to do so, to check whether current time is greater or equal to the tmin, etc. And then I perform the second lookup on the XFSM table based both on the current state, the result, and the conditions. For the tables, it's the same, we just add the registers in the tables. So again, just a screenshot for this application. I send 100 packets from the client, and on the server I got the first 6 packets. My token bucket had a capacity of 5 tokens. So first packets come through, then we have to wait each time that a new token is generated again, so that the next packet may arrive. All of the packets are dropped. So, okay. So this is just a list of some additional use case for OpenState and Rpp. For the project, we use it to do quality of service, to do failure detection and recovery, and also there's an application I appreciate quite a lot, which is denial of service detection and mitigation. So I won't describe it here. For the details, I have some blog articles if you want to read them on some of these use cases. And to conclude, we think that eBPF makes a nice target for the Rpp architecture. So both OpenState and Open Packet Processor. We have some limitations with this implementation. So, for example, we have no wildcarding mechanism yet in BPF. So if I want to say, okay, now I want to match a packet with anything for the UDP destination port, and I just want to focus on the source port. Currently, it's a bit difficult to do with BPF. There's also the problem for concurrent accesses. If I want to run my stateful application on several cores at a time, the packet won't necessarily be processed and access to the maps in the same order as they arrive. But otherwise, globally, it looks quite well. So we have more implementations of this OpenState architecture for the BIBA project. The eBPF is just a small subset of what we've done. So if you want to go and have a look, the reference implementation is done over virtual switch, which is off-soft switch. It's accelerated with the PFQ framework. There are also several other implementations and acceleration prototypes. I know that some partners are running OpenState on top of their Polmod driver for DPDK on FPGA. So also everything is available on GitHub if you want to have a look at this. So that's it. Thank you. If you want to see more details about some of these points, including the deliverables of the project, you can go and see them. No problem. If you have questions, I will be glad to answer them. Yeah?
So what is the real performance? For example, the load balancing does compared to IPS?
So what's the real performance? Depends on what implementation you run. For eBPF, I take it, I've not finished performance tests yet, but it uses eBPF facilities, so it will be the same as eBPF with TC. I think the features that are available for eBPF was for simple drop with TC, eBPF TC. It was something like 4 and something million packets per second on 3.7 gigahertz processor, I think. So it will not be as fast as this because we use maps, we use hash maps, so we have to hash values, and of course it will be slower than this. But still, I think we can get pretty good performances. I think I forgot a point for the next step. So next step include trying this with XDP hooks so as to attain better performances, hopefully. Any other question? Thank you. Thank you.